right now as you watch this video. You're falling through a hole in space that stretches 2 billion light years across. This is not science fiction, this is not speculation. In 2013, astronomers confirmed what many had suspected for decades. Our galaxy, the Milky Way, along with everything within hundreds of millions of light years, sits inside one of the largest empty regions ever discovered in the observable universe. Scientists call it the KBC void, named after the 3 researchers who measured its boundaries, and most people walking the streets today have absolutely no idea it exists. The discovery came from a simple question with a terrifying answer. When astronomers counted the galaxies surrounding Earth in every direction, the numbers came up wrong, not slightly wrong, dramatically wrong. There were significantly fewer galaxies than there should be, stretched across an incomprehensible volume of space, with our tiny planet floating somewhere near the center of this cosmic emptiness. The implications of this finding have sent shockwaves through astrophysics that continue reverberating today. You see, our entire understanding of the universe rests on an assumption that has guided cosmology for nearly a century. We call it the cosmological principle, and it states something profound. No matter where you are in the universe, if you look out far enough, everything should look roughly the same. The cosmos should be uniform, with no special locations and no privileged observers. Earth is not the center of the solar system, the sun is not the center of the galaxy, the Milky Way is not the center of anything. We have progressively decentered humanity's position in the cosmos across generations of scientific discovery, but now we face an uncomfortable possibility. What if we do occupy an unusual location? What if our measurements of the universe's most fundamental properties have been systematically biased by the cosmic hole we call home? This is not merely an academic curiosity. The expansion rate of the universe, one of the most precisely measured quantities in all of physics, appears to be different depending on how you measure it. When astronomers look at the ancient light from the beginning of time and calculate how fast the universe should be expanding today, they get one number. When they look at nearby supernovae and directly measure how fast galaxies are receding, they get a different number. The disagreement is about 9%, and that might sound small, but in the world of precision cosmology, it represents a 5 sigma discrepancy. There is less than a 1 in a million chance this disagreement is due to random measurement error. Something is genuinely wrong, either with our measurements, our models, or our fundamental understanding of the cosmos. The void offers an elegant solution to this crisis. If we live inside a massive underdense region, the local expansion rate we measure would naturally appear faster than the true cosmic average. Matter surrounding the void pulls outward on everything inside it, adding extra velocity to the recession of galaxies. We would not be measuring the universe incorrectly, we would be measuring it from inside a hole where the rules appear different than they actually are. The universe, in a very real sense, may be lying to us about how fast it is growing, and the lie stems from our cosmic address. But this solution comes with its own unsettling implications. A void as large and as deep as the KBC void should be extraordinarily rare. Computer simulations that recreate the evolution of the universe from the Big Bang to today almost never produce structures this extreme. Some calculations suggest the statistical probability of such a void existing at all is less than 1 in 1,000. Others place it at 10 sigma, meaning you might not find a single void this large in the entire observable universe. Yet here we are, living inside one. Either we have won a cosmic lottery of absurd proportions, or our models of how structure forms in the universe are fundamentally incomplete. Tonight, we journey into the heart of cosmic emptiness. We will explore how astronomers discovered this void, what it means for our understanding of the universe's structure, why it threatens to overturn decades of precision cosmology, and what it reveals about our strange and unlikely position in the cosmos. Along the way, we will traverse the largest structures ever discovered, encounter galaxies that evolve in profound isolation, and confront the possibility that the universe we see from Earth is not representative of the universe as a whole. If you find yourself questioning everything you thought you knew about our place in the cosmos, you are not alone. The scientists who made this discovery are still grappling with its implications. But one thing has become increasingly clear: the universe is far stranger than we ever imagined, and our location within it may be one of the strangest things of all. If you are ready to see the cosmos in an entirely new light, hit that like button and subscribe. Prepare yourself. We begin. The story begins in 2013 when 3 astronomers were engaged in what might seem like a tedious task, counting galaxies. Ryan Keenan, Amy Barger and Lennox Cowie were working with data from multiple galaxy surveys, attempting to map the 3-dimensional distribution of matter in our cosmic neighbourhood. Their methodology was straightforward. Measure the positions of galaxies at various distances from Earth. Compare the observed number density to what cosmological models predict. Look for any systematic deviations. What they found was impossible according to standard cosmology. Everywhere they looked within about 1 billion light-years of Earth, there were fewer galaxies than expected. This was not a subtle deficit appearing in one direction or at one particular distance. The underdensity extended in every direction simultaneously, forming a sphere of cosmic emptiness with our galaxy floating somewhere near its centre. The numbers were stark. Depending on the measurement technique and distance range examined, the matter density within this enormous volume registered at roughly 50 to 80% of the cosmic average. A significant fraction of the matter that should exist in our neighbourhood had somehow gone missing. The researchers triple-checked their data. They used multiple independent galaxy surveys. They examined the sky from different angles and at different wavelengths. The result remained consistent. Our galaxy and everything around it sits inside an underdense bubble of space so massive it dwarfs everything else humans have ever observed. To appreciate the scale, consider that the entire Milky Way, with its hundreds of billions of stars, could fit inside this void approximately 10 million times. The void stretches so far that light travelling since the era of the dinosaurs would still be crossing it today. The discovery earned a name using the initials of its 3 discoverers, the KBC void. Some astronomers also call it the local hole, emphasizing that it represents a deficiency in cosmic matter rather than a complete absence. But there is nothing casual about what this structure represents for our understanding of the universe. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Yes, galaxies cluster together into groups and clusters. Yes, those clusters arrange themselves along filaments separated by relatively empty regions. This is the cosmic web, the large-scale structure of the universe that emerged from tiny density fluctuations in the early cosmos. But the fluctuations should be statistical in nature. On average, any sufficiently large volume should contain approximately the same amount of matter as any other sufficiently large volume. The KBC void violates this expectation with alarming significance. Computer simulations of how the universe evolved from the Big Bang to today use our best understanding of physics to recreate cosmic structure formation. Scientists have run thousands of these simulations, each representing a possible version of our universe with slightly different initial conditions. When researchers search these simulated universes for voids as large and as deep as what we observe around Earth, they find very few matches. The statistical likelihood varies depending on the specific assumptions, but estimates range from exceptionally rare to effectively impossible. One analysis calculated that the KBC void represents approximately a 10 sigma deviation from expected density fluctuations. To put this in perspective, physicists typically consider 5 sigma the threshold for a definitive discovery. Finding a 5 sigma result means there is less than a 1 in 3.5 million chance the observation is due to random chance. 10 sigma is so unlikely that standard statistical tables do not even bother calculating it. You would need to survey trillions of universe-sized volumes before expecting to encounter even one such void by random chance. Yet here we sit, inside exactly such a structure. The implications cascaded immediately from this discovery. If we reside in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to calculate how fast the universe expands, are we seeing the true cosmic expansion rate? Or are we measuring a distorted local version, warped by the cosmic hole surrounding us? The void hypothesis offered an answer to one of the most vexing mysteries in modern cosmology, a puzzle known as the Hubble tension. For years, scientists have measured 2 different expansion rates depending on whether they examine the ancient universe or the nearby universe. The numbers disagree by approximately 9%, which sounds small but represents a genuine crisis. Both measurements are incredibly precise, with very small error margins. Both methods have been tested, retested, and confirmed by the independent research teams. Both should give the same answer if our cosmological models are correct. They do not. If Earth sits inside a massive underdense region, the resolution becomes clear. gravity from the denser matter surrounding the void would pull outward on galaxies within it. This adds extra velocity to their motion away from us, making the local expansion appear faster than the cosmic average. We are not measuring the universe incorrectly. We are measuring it from inside a hole, where apparent expansion is genuinely faster than elsewhere. This realization changed everything. But it also raised an uncomfortable question that cosmologists continue grappling with today. If our location is this unusual, can we trust anything we think we know about the cosmos? The measurements that revealed the age of the universe? The amount of dark matter, the strength of dark energy? All of these derive from observations made from inside the void. How much of what we believe about the universe reflects cosmic truth, and how much reflects our peculiar vantage point? More recent observations have strengthened the case for the void's existence. In July 2025, researchers analysing 20 years of data from baryon acoustic oscillation measurements presented their findings at the Royal Astronomical Society's National Astronomy meeting in Durham. These measurements used the imprint of sound waves from the early universe to trace cosmic expansion history with extraordinary precision. According to their analysis, a void model is approximately 100 million times more likely than a void-free model consistent with standard cosmology. The statistical weight of this finding is remarkable, suggesting that the evidence for a local underdensity has become difficult to dismiss. The evidence continues mounting with each new survey and each new measurement technique. The Discovery team has also found that their void model successfully predicts other observed phenomena. The bulk flow of galaxies, meaning the coherent motion of matter across hundreds of millions of light years, matches predictions from the void hypothesis. Galaxies within and around the void move in patterns consistent with the gravitational influence of a massive underdensity. These predictions were made before the observations confirmed them, lending additional credibility to the void explanation. But not all cosmologists accept this interpretation. Some argue that even a void as large as the KBC void cannot produce effects strong enough to fully explain the Hubble tension. Others point out that finding ourselves in such an unusual location seems suspiciously convenient, violating the spirit of the cosmological principle that has served physics so well. Perhaps we are interpreting the data incorrectly. Perhaps there are systematic measurement errors we have not yet identified. Perhaps the universe is more inhomogeneous on large scales than we previously assumed, making large voids less surprising. The controversy remains unresolved, which is why the Hubble tension continues to be described as a crisis deal rather than a solved problem. It is not just a number that disagrees with another number. It is a signal that our understanding of the cosmos may be fundamentally incomplete, and the void we call home sits at the centre of this ongoing scientific drama. To understand our cosmic predicament, we first need to understand what a void actually is. The name might conjure images of absolute nothingness, regions of space completely devoid of matter, where light travels endlessly without encountering a single atom. But cosmic voids are not truly empty. They are relatively empty, containing far less matter than average while still hosting scattered galaxies' dark matter. And the mysterious substance we call dark energy. Think of it this way. If a typical region of space contains 10 galaxies within a given volume, the same volume inside a void might contain only 1 or 2. The galaxies do not vanish completely. They become rare, scattered islands in an ocean of near-nothingness. Between these lonely galaxies stretches space that contains primarily dark matter, dark energy, and occasional wisps of hydrogen gas so diffuse that individual atoms might be separated by meters or more. The density inside a void varies depending on location. At the void's centre, where matter is most scarce, densities can drop to approximately 15% of the cosmic average. Moving toward the edges, density gradually increases until you reach the surrounding walls of the cosmic web, where matter concentrates into filaments and clusters. The transition zone between void and wall is remarkably sharp. Density can jump from 10% of average in the void interior to more than 100% in the surrounding structure over relatively short distances. This low density has profound consequences for physics. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to produce noticeable effects. In a void where mass is scarce, gravity becomes even less relevant to cosmic dynamics. Without enough matter to pull things together, the dominant force becomes something else entirely: dark energy. Dark energy is the mysterious substance that makes up approximately 68% of the universe's total energy content. Unlike matter, which attracts other matter through gravity, dark energy exerts a repulsive pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing the expansion in those areas. The matter pulls inward while space tries to push outward, and the result is a dynamic tension. Inside voids, gravity loses this tug-of-war decisively. With insufficient matter to counteract dark energy's influence, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls containing the emptiness. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes relative to its surroundings. The emptier it becomes, the weaker gravity's influence grows. The weaker gravity grows, the faster expansion proceeds. Voids are runaway structures, destined to become ever more dominant features of cosmic architecture. Scientists have confirmed this through careful observation. By measuring how galaxies near void edges move compared to galaxies in denser regions, astronomers can detect the void's influence. Galaxies at the void boundary are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward, and that something is gravity pulling from outside the void. This might sound counterintuitive. If gravity pulls, how can it push galaxies outward? The answer lies in geometry. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means pulling you away from the valley center. Inside a cosmic void, the situation is analogous. All the matter lies outside the void in the surrounding filaments and clusters. That exterior matter gravitationally attracts the interior material, pulling galaxies outward from the void center toward denser regions beyond. The result is an outflow pattern, a systematic movement of galaxies accelerating away from the underdense region. This outflow is measurable and significant. Our own Milky Way participates in it. According to the measurements by astronomers including Brent Tully, we are moving away from the nearby local void at approximately 600,000 miles per hour, driven by exactly this gravitational imbalance. This motion is separate from cosmic expansion. It is peculiar velocity, meaning it results from local gravitational effects rather than the stretching of space itself. When combined with other gravitational influences, including the pull from the Virgo cluster and the Great Attractor, our galaxy's total peculiar velocity relative to the cosmic microwave background reaches approximately 627 kilometers per second. The interior of a void becomes a strange place for physics. Light travels through it, experiencing less gravitational influence than light passing through normal space. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity causes less gravitational redshift, showing up as cold spots in temperature maps of the early universe. These cold spots align with where we observe large voids today. The alignment is not coincidence. It is physics revealing the hidden structure of the cosmos. Understanding what makes voids empty helps explain why they matter so much to cosmology. They are not just boring blank spaces between interesting galaxy clusters. They are laboratories where dark energy dominates and gravity takes a back seat. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works. The void around us might be unsettling because it makes us question our cosmic typicality, but it also offers a rare opportunity. We are positioned in exactly the right place to study the universe's most extreme low-density environments from the inside. Step back far enough and the universe reveals its true structure. What appears as random scatter when you look at individual galaxies transforms into something far more organized when you survey billions of light years at once. Galaxies are not distributed uniformly through space. They arrange themselves along vast filaments that stretch across hundreds of millions of light years, connecting at nodes where massive galaxy clusters form. Between these filaments lie the voids, enormous bubbles of near emptiness that make up the majority of cosmic volume. Scientists call this structure the cosmic web, and it represents the largest organization of matter in existence. Picture a sponge, or perhaps Swiss cheese. The material concentrates into thin walls and strings, while the interior consists mostly of hollow pockets. Now expand that image to fill the observable universe. The walls become filaments containing thousands of galaxies. The pockets become voids spanning hundreds of millions of light years. At the intersections where multiple filaments meet, you find the densest regions of all, massive galaxy clusters containing trillions of stars bound together by gravity. This structure was not always obvious. For decades, astronomers photographed the sky and catalogued galaxies, but they saw only two-dimensional positions projected onto the celestial sphere. Galaxies that appeared next to each other might actually be separated by billions of light years, with one much farther from Earth than the other. The true three-dimensional arrangement remained hidden. Everything changed when scientists began measuring galaxy redshifts systematically in the 1970s and 80s. Redshift provides a crucial piece of information: distance. As the universe expands, light travelling through space gets stretched to longer wavelengths. The more space light traverses, the more stretching occurs. By measuring how much a galaxy's light has been redshifted, astronomers can calculate how far away it lies. Suddenly, the distribution snapped into focus. The universe had structure on scales nobody had anticipated. The first major void discovery came in 1998 when two independent teams identified large underdense regions in their redshift surveys. More surveys followed, each probing deeper into space and revealing an increasingly intricate web. The Sloan Digital Sky Survey, which began observations in 2000, created spectacular three-dimensional maps spanning billions of light years. These maps show the cosmic web in stunning detail, with filaments twisting and branching like blood vessels while voids appear as dark bubbles sometimes 500 million light years across. Some of the structures discovered defy easy comprehension. The Sloan Great Wall is a galaxy filament nearly 1.4 billion light-years long, among the largest structures in the observable universe. The Hercules Corona Borealis Great Wall, discovered in 2013 using gamma-ray bursts as reference points, stretches more than 10 billion light-years across, challenging our understanding of how such enormous structures could form. On the opposite end of the scale, supervoids like the one in the constellation Eridanus stretch nearly 2 billion light-years wide with even fewer galaxies than the KBC void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted when cosmology began as a modern science. Why does the universe organize itself this way? The answer reaches back to the very beginning. Immediately after the Big Bang, matter was not perfectly uniform. Quantum fluctuations during inflation, the brief period of exponential expansion in the universe's first fraction of a second, created tiny variations in density. Some regions ended up slightly denser than average, others became slightly less dense. These differences were minuscule, perhaps 1 part in 100,000. But gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into protogalaxies, which combined into galaxy clusters, which aligned into filaments. Meanwhile, the underdense regions expanded into voids, their matter draining away toward the growing concentrations. The cosmic microwave background provides a snapshot of these density variations when the universe was only 380,000 years old. At that time, the variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree. Warmer spots had slightly higher density, cooler spots had slightly lower density. Satellites like the Planck spacecraft have mapped these temperature variations across the entire sky with exquisite precision. The maps reveal the seeds from which all cosmic structure grew. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. The results reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we actually observe. The match between prediction and observation is one of the great triumphs of modern cosmology. It confirms that our understanding of how gravity shapes structure over cosmic time is largely correct, but the simulations rarely produce voids as large or as deep as the KBC void. This is where tension arises. The initial quantum fluctuations were random, so every region had some chance of ending up as either a void or a filament. Probability distributions matter. Small voids should be common because they arise from common, small fluctuations. Large voids should be less common because they require larger, rarer fluctuations. Extremely large voids should be vanishingly rare. requiring initial conditions so unusual that standard cosmology struggles to explain them. The KBC void appears to fall into that final category. Its existence challenges our understanding of structure formation and forces us to consider possibilities that make cosmologists uncomfortable. Either we got extraordinarily lucky in our cosmic placement, or something is missing from our models of how the universe evolved from uniformity to complexity. Today, voids occupy roughly 80 to 90% of the total volume of space. Filaments and clusters make up the remaining fraction, but contain most of the mass. This imbalance defines the character of our cosmos. We live not in a universe filled with galaxies, but in a universe of emptiness punctuated by occasional concentrations of matter. The cosmic web is mostly holes, with the interesting stuff confined to the walls between them. The KBC void is just one bubble in this cosmic foam, but it happens to be our bubble, and that makes all the difference for what we observe and how we interpret the universe around us. Pinpointing exactly where we sit inside the KBC void requires careful measurement and some humbling perspective on scale. The Milky Way is not at the void's centre, but it is close enough to matter significantly. Current measurements place our galaxy somewhere between 200 and 400 million light-years from the void's approximate centre. That might sound like an enormous offset, and by any human standard it certainly is. But the void extends outward for roughly 1 billion light-years in every direction from its centre. Our displacement represents only a modest fraction of the total volume. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. This position is not random. It has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely, perhaps in one of the dense filaments that crisscross the cosmic web, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension might not exist as a scientific puzzle at all. Our larger cosmic neighbourhood adds layers of complexity to this picture. The Milky Way belongs to the local group, a collection of more than 80 galaxies that includes our giant neighbour Andromeda, along with dozens of smaller dwarf galaxies bound together by mutual gravity. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. The name Laniakea comes from Hawaiian and means immense heaven, an apt description for a structure of such grandeur. The entire supercluster moves coherently, drawn toward a gravitational focal point that astronomers have named the Great Attractor. This mysterious concentration of mass lies hidden behind the obscuring dust of our own galaxy's plane, making direct observation difficult, but its gravitational influence is unmistakable. Everything within Laniakea flows toward it like water draining toward a basin. Here is the paradox that should give you pause. Laniakea, despite containing 100,000 galaxies spanning 500 million light-years, resides entirely within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. The void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population scattered through the void, one of the rare concentrations in an otherwise barren expanse. The scales involved here transcend ordinary comprehension. We are not discussing neighbourhood underdensities or gaps between nearby clusters. We are discussing a cosmic desert so enormous that structures containing billions upon billions of stars register as mere specks within its volume. The local group is also influenced by another nearby void, distinct from but connected to the larger KBC structure. This local void extends about 200 million light-years and sits adjacent to our position. Our galaxy is rushing away from it at roughly 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond. This motion combines with other gravitational influences to produce our galaxy's total peculiar velocity. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows exceeding predictions from standard cosmology. Entire regions of space are moving faster than models say they should, flowing in coherent patterns driven by the void's gravitational imbalance. The KBC void creates a large-scale velocity field affecting everything within it. Galaxies are not just sitting passively in an empty region and expanding with the universe, they are actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. This makes our local patch of the universe more dynamic and unusual than the calm, uniform cosmos that standard models assume. We are not observing from a typical location. We are observing from inside one of the cosmic web's most extreme features. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. That light experiences less gravitational interaction than light traveling through denser regions. The reduced gravity creates subtle effects on the light's wavelength and energy. Additionally, the void itself influences the distribution of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range. Beyond the shell, the universe returns to more typical density. This creates an observational bias that cosmologists must carefully account for. We are not sampling a random location in the universe. We are sampling from inside one of its most extreme features, and that sampling location affects everything we measure. Living in the void means living with systematic uncertainty about how representative our measurements truly are. Recent research has begun mapping our cosmic neighborhood with unprecedented precision. In October 2024, a team led by Brent Tully at the University of Hawaii reported that Laniakea itself might be part of an even larger structure. Their measurements of galaxy flows suggest that Laniakea, along with neighbouring superclusters like Apus and Coma, may all be falling toward an enormous basin of attraction centred on the Shapley concentration. This structure, roughly 10 times the volume of Laniakea, could be the true gravitational anchor of our cosmic region. If confirmed, it would mean that even our understanding of Laniakea's extent was incomplete. Understanding Laniakea's structure and motion helps clarify our position within the larger void. We are not at the void centre in complete isolation. We are offset from the centre, situated in a moderately dense region that is nonetheless underdense compared to cosmic averages. Laniakea represents a significant concentration of matter within the void, but it is not enough to eliminate the void's overall deficiency. The paradox resolves when you realise that large-scale and small-scale structures coexist. The void describes average properties over billions of light-years. Laniakea describes local properties over hundreds of millions of light-years. Both are real, and both matter for different aspects of cosmology. Every measurement you have ever heard about the universe's expansion rate might be wrong, not because scientists made mistakes, but because we are measuring from inside a cosmic hole that distorts the signal. The problem has a name that sounds almost innocent: the Hubble tension. But what started as a puzzling discrepancy has grown into a full-blown crisis threatening to overturn decades of precision cosmology. The crisis centres on a number called the Hubble constant, which tells us how fast space itself is stretching. Edwin Hubble discovered this expansion nearly a century ago, when he observed that distant galaxies are receding from us, with more distant galaxies receding faster. The relationship is remarkably clean. Velocity equals the Hubble constant times distance. Double the distance, double the recession velocity. Cosmologists measure this constant through two fundamentally different approaches, and the approaches disagree in ways that cannot be explained by the measurement error. The first method looks at the cosmic microwave background, ancient light released when the universe was only 380,000 years old. This radiation carries encoded information about the early universe's density and expansion rate. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The Planck satellite performed the most precise version of this measurement, arriving at a Hubble constant of approximately 67 km per second per megaparsec. That means for every megaparsec of distance, roughly 3.26 million light-years, space expands by 67 kilometers every second. The second method looks at nearby objects with known brightness. Type Ia supernovae serve as cosmic standard candles because astronomers understand exactly how bright they should be. By comparing actual brightness to apparent brightness as seen from Earth, scientists calculate distance. Cepheid variable stars provide another rung on this cosmic distance ladder. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently produces a higher number, approximately 73 km per second per megaparsec. The discrepancy is about 9%. Both measurements carry very small error margins, Both have been confirmed by independent teams using independent data. The disagreement has reached 5 sigma statistical significance, meaning there is less than a 1 in a million chance it is random variation. Something real is happening. Either one or both measurement methods have hidden systematic errors, or our models of the universe are missing something fundamental. In February 2024, the James Webb Space Telescope provided crucial validation. Nobel laureate Adam Rees and his team used Webb's sharper vision to measure the same Cepheid variable stars that Hubble Space Telescope had observed. The new data confirmed that Hubble's measurements were accurate. There was no hidden error from stellar crowding or other systematic effects that skeptics had proposed. The local expansion rate is genuinely higher than the cosmic microwave background predicts it should be. The void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we are measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region. This inflates the local Hubble constant measurement. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. The cosmic microwave background method remains unaffected because it probes the early universe long before voids formed. That measurement might be the accurate one for the universe's global properties. This resolution has profound implications. Most headlines you have seen about the accelerating universe and dark energy might be describing a local phenomenon rather than a universal truth. We have spent decades building cosmological models based partly on local expansion measurements, and those measurements might be systematically biased by our location. Not all cosmologists accept this conclusion. Some resist because it violates the cosmological principle. Finding ourselves inside a super void that significantly affects our measurements seems to contradict the idea that Earth does not occupy a special location. Science has progressively decentered humanity from special cosmic positions. Copernicus removed Earth from the center of the solar system. Later observations showed the Sun is not centrally located in the galaxy. Now we are supposed to believe we just happen to live inside one of the largest voids ever observed. The statistical improbability bothers many researchers deeply. Yet the evidence keeps mounting. The void exists. Our measurements disagree. The void's predicted effects match the observations. Whether scientists like the implications or not, the universe might actually be misleading us about its expansion rate through no fault of its own. Our location causes us to misinterpret what we measure. In January 2025, researchers from Duke University published new measurements using the Coma cluster as a distance anchor. Their value for the Hubble constant came out to 76.5 kilometers per second per megaparsec, even higher than previous local measurements. The lead author, Dan Skolnick, stated bluntly that our model of cosmology might be broken. The discrepancy has grown so severe that some scientists argue the term tension no longer captures the problem's seriousness. It is now a crisis. The crisis matters because the expansion rate determines everything else about cosmic history. If the universe expands faster, it reaches its current size in less time, making the universe younger. Current calculations based on the cosmic microwave background put the universe's age at 13.8 billion years. But if the higher local measurement applied globally, the universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters that appear to be 13 billion years old based on stellar evolution models. These stars would be older than the universe itself, which is impossible. Either our stellar age measurements are wrong, our understanding of stellar physics is wrong, or the higher Hubble constant does not apply universally. None of these options offer comfort. The void hypothesis provides a way out. If our local measurements are inflated by our unusual location, the cosmic microwave background estimate of 13.8 billion years could be correct. The universe would be old enough for the observed stars to exist. This resolution requires accepting that we live in an unusual location, which bothers scientists philosophically, but it avoids requiring major changes to stellar physics or fundamental cosmology. The controversy will not be resolved soon. Future observations extending well beyond the void will test whether the Hubble constant truly varies with distance as the void hypothesis predicts. If distant regions confirm our local conclusions, we might need entirely new physics. If they show systematically lower expansion rates, the void explanation gains strength. Either outcome will reshape our understanding of the cosmos. The Hubble tension is not just a puzzle waiting to be solved. It is a window into the possibility that the universe is fundamentally different from what we have believed for generations. Inside a void, gravity does something counterintuitive. It pushes outward instead of pulling inward. This is not because gravity itself reverses. The force of gravity always attracts mass toward mass, but geometry matters, and the geometry of a void creates apparent repulsion. Imagine standing in a shallow valley, surrounded by mountains on all sides. Gravity pulls you towards the mountains, which means pulling you away from the valley's center. Now scale this image up by hundreds of millions of light years. Inside a cosmic void, galaxies experience the same effect. All the mass lies outside the void, concentrated in the surrounding filaments and clusters. That exterior matter gravitationally attracts everything inside, pulling galaxies outward from the void center toward denser regions beyond. The result is an outflow. Galaxies near the void center are accelerating away from it, moving toward the massive structures that surround the emptiness. The effect is strongest near the void center, where the gravitational gradient is most pronounced, and weakens toward the edges, where matter density increases. For the KBC void specifically, this outflow adds hundreds of kilometers per second at galaxy velocities. Our own galaxy participates in this pattern. The Milky Way is not sitting still in space. It is plummeting through the cosmos at approximately 600,000 miles per hour relative to the local void, driven by the gravitational imbalance between the emptiness behind us and the denser structures ahead. This speed is difficult to comprehend. At 600,000 miles per hour, the Milky Way travels about 107 miles every second. In a single year, our galaxy moves roughly 5.2 billion miles through space relative to the void. That sounds enormous by any human standard, but the void is so vast that our motion barely registers against its scale. It would take hundreds of millions of years to cross from one side of the void to the other, even at this breakneck pace. Meanwhile, the void continues expanding due to cosmic acceleration and dark energy, growing faster than we could ever escape. We are inside the void now, and we will remain inside it for the foreseeable cosmic future. The local sheet adds another component to our motion. This flattened structure of galaxies includes the Milky Way, Andromeda, and other nearby galaxies. The entire sheet forms one wall of the local void. The whole structure is rushing away from the void center at about 260 kilometers per second, roughly 580,000 miles per hour. Our galaxy participates in this bulk motion along with its neighbors. The sheet is actively being evacuated from the void region, flowing outward like water draining from a depression. But there is more to our velocity than just escaping voids. The Milky Way is also falling toward the Virgo cluster, a rich concentration of galaxies about 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and has enough mass to gravitationally attract everything in the surrounding region, including us. This adds roughly 250 kilometers per second to our peculiar velocity, directed toward Virgo. Meanwhile, the Milky Way and Andromeda are falling toward each other and will collide in about 4 billion years, adding yet another velocity component. When you sum all these gravitational influences, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame comes to about 627 kilometers per second. That is the velocity astronomers measure when they examine the dipole pattern in the cosmic microwave background temperature. We are not stationary observers watching the universe expand around us. We are hurtling through space at tremendous speed, pushed and pulled by the gravitational gradients on the scales that dwarf anything in human experience. These motions matter because they complicate cosmological measurements. When we observe distant galaxies and measure their redshift, we need to correct for our own motion. Otherwise, galaxies in the direction we are moving appear blue-shifted, while galaxies in the opposite direction appear red-shifted, creating false patterns that could be mistaken for cosmic structure. Astronomers have known about these corrections for decades and routinely apply them. But inside a void, the corrections become more complicated. The void creates large-scale bulk flows extending over hundreds of millions of light years. Disentangling the void effect from true cosmic expansion requires careful modelling of the local velocity field. The problem compounds at different distance scales. Close to the void centre, outflow is rapid. Farther from the centre, outflow slows. Beyond the void edge, peculiar velocities might even reverse as matter falls back toward denser filaments. This creates a complicated velocity profile varying with distance. When astronomers measure the Hubble constant using supernovae at different distances, they are sampling this varying velocity field. If most of their supernovae lie within the void, which they do because we deliberately avoid using extremely distant supernovae due to other complications, the measurement gets boosted by the outflow. The model predicts that the measured Hubble constant should appear to decrease with the distance. Close measurements show the highest values, influenced most strongly by the void. More distant measurements should show progressively lower values as the void's influence fades. Recent observations confirm exactly this trend, lending credibility to the void explanation for the Hubble tension. Our high speed through space is itself evidence for the void. If we lived in a typical region with average density, our peculiar velocity would be much smaller, perhaps 100 or 200 kilometers per second at most. The fact that we are moving so fast indicates strong gravitational gradients in our vicinity, exactly what you would expect from being near a large underdense region. The velocity is consistent with the void hypothesis and would be difficult to explain without it. The cosmological principle is one of the foundational assumptions of modern physics. It states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special or different from any other when you average over large regions. Isotropic means the same in all directions. The universe looks identical no matter which way you look. These assumptions simplify the mathematics of cosmology enormously. They allow scientists to model the entire universe using relatively straightforward equations. Without the cosmological principle, the equations become vastly more complicated, and predictions become nearly impossible. The principle has been remarkably successful, accurately describing many observations over nearly a century of precision cosmology. But the KBC void represents a major violation of homogeneity. If the void truly spans 2 billion light-years with a 20% density deficit, that is an enormous inhomogeneity. Even on cosmic scales, the void is not small compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling, we happen to live near the centre of this abnormal structure, which seems to contradict the idea that our location is unremarkable. Throughout scientific history, discovery has progressively moved Earth from special positions. Copernicus showed Earth was not the centre of the solar system. Later observations revealed the Sun orbits far from the galactic centre. The galaxy itself occupies no privileged location in the cosmos. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the centre, but there is no centre at all because every location is equivalent. The void challenges this worldview directly. If we live inside an abnormally large underdense region, our location is unusual by definition. Voids exist throughout the universe, but most are smaller than the KBC void. Supervoids this large are statistically rare. Finding ourselves in one raises uncomfortable questions about whether the cosmological principle truly holds, or whether it is only approximately true on scales much larger than previously assumed. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare, perhaps a 10 sigma statistical deviation. In a typical random realization of cosmic structure formation, you might not find even one such void anywhere in the observable universe. Yet here we sit inside exactly such a structure. This suggests one of three possibilities. First, we might be incredibly lucky. The universe had to develop structure somewhere, and by pure chance we ended up in one of the most extreme underdensities to form. This explanation preserves the standard model but requires accepting astronomical coincidence. Second, the void might not be as extreme as measurements suggest. Different observational techniques have produced somewhat different results. If the true deficit is closer to 10 or 15% rather than 20%, the statistical improbability becomes less severe. The void remains challenging but not impossible to explain. Third, our cosmological models might be missing something fundamental about structure formation. If gravity works differently on large scales than general relativity predicts, or if dark matter behaves in ways we have not anticipated, large voids might form more easily than current simulations suggest. Defenders of the cosmological principle offer several counterarguments. They note that homogeneity only applies at scales of several hundred megaparsecs or larger. The void is about 600 megaparsecs across, right at the edge of where homogeneity should kick in. Perhaps the universe is simply less smooth at those scales than we assumed. Others invoke anthropic reasoning. Observers can only exist in certain types of environments. Intelligent life requires galaxies to form, and galaxies form preferentially in moderately dense regions, rather than in the densest clusters or emptiest voids. If most observers live in mildly underdense regions, finding ourselves in a slight void should not surprise us. But this argument only works if the KBC void is not as extreme as it appears. A 20% deficit pushes the boundaries of what anthropic selection can plausibly explain. Some researchers have proposed that resolving these puzzles might require modifications to our theory of gravity. Modified Newtonian dynamics, or MOND, was originally proposed in 1983 to explain galaxy rotation curves without invoking dark matter. Under MOND, gravity behaves differently when accelerations are extremely small. On cosmological scales, this enhanced gravity would make structure formation more vigorous, producing deeper voids more easily. Simulations using MOND-like gravity naturally create voids as large as the KBC void without requiring unusual initial conditions. However, MOND faces serious challenges explaining other observations, particularly the cosmic microwave background and gravitational lensing. It is not a complete replacement for the standard model, but its success at predicting void statistics suggests that something about standard gravity on large scales might need revision. The debate over the cosmological principle will not be settled by argument alone. Future observations will help resolve it. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict or more common than expected. If big voids turn out to be frequent, the cosmological principle survives, but the standard model needs revision. If they remain truly rare, we need to explain why we happen to live in one. The stakes extend beyond abstract philosophy. If our location systematically biases our measurements, then conclusions we have drawn about the universe's fundamental properties might need revision. The age of the universe, the amount of dark matter, the nature of dark energy, all of these derive from observations made from inside the void. How much of what we believe reflects cosmic truth, and how much reflects the peculiarities of our cosmic address? The KBC void is not the only immense emptiness that astronomers have discovered. Several other voids of comparable or even larger scale exist within the observable universe, each presenting its own puzzles and each challenging our understanding of cosmic structure. Perhaps the most famous is the Bootes void, discovered in 1981 by astronomer Robert Kirshner during a survey of galaxy redshifts. Located approximately 100 million light-years from Earth in the direction of the constellation Bootes, this void spans roughly 30 million light-years across. Within this enormous volume, astronomers have found only about 60 galaxies, far fewer than the 2,000 or more you would expect in a typical region of equivalent size. The Bootes void earned the nickname the Great Void for good reason. Its centre is so empty that astronomer Greg Oldering once remarked that if the Milky Way had formed at the centre of the Bootes void, we would not have known other galaxies existed until the 1960s. The isolation would have been so profound that for most of human history, astronomers looking outward would have seen essentially nothing. The handful of galaxies that do exist inside the Bootes void are not randomly scattered. They lie in a tube-like structure running through the void's interior, suggesting that this supervoid may have formed through the merger of several smaller voids. Like soap bubbles combining into a larger bubble, smaller voids would have joined together over cosmic time, leaving behind remnant structures where their walls once met. Even more intriguing is the Eridanus supervoid, located in the direction of the constellation Eridanus. Based on measurements from the Dark Energy Survey and earlier observations too, this void stretches approximately 1.8 billion light-years across and lies with its centre roughly 2 to 3 billion light-years from Earth. The void contains approximately 30% less matter than the surrounding cosmic average, making it one of the most significant underdensities in our galactic neighbourhood. The Eridanus supervoid was discovered through its impact on the cosmic microwave background radiation. In maps of the CMB temperature, a conspicuous cold spot appears in the direction of Eridanus, approximately 5 degrees across on the sky and roughly 70 millionths of a Kelvin colder than average. While typical CMB fluctuations exist at all scales, this cold spot is unusually large and unusually cold. Its statistical probability is low enough that cosmologists have debated its origin for nearly 2 decades. One explanation involves the integrated Sachs-Wolf effect. When light from the CMB passes through a large void, it loses energy. As photons enter the void, they must climb a gravitational hill because they are transitioning from a high-density region to a low-density region. Normally, they would regain this energy when exiting the other side. But if dark energy stretches the void while the light is passing through, the hill becomes flatter by the time the photons exit. They cannot regain all the energy they lost, emerging slightly cooler than before. This effect should produce exactly the kind of cold spot we observe. The Dark Energy Survey confirmed in 2021 that a significant underdensity does exist in that direction, strengthening the connection between the void and the cold spot. Their analysis found that the Eridanus supervoid appears as the most prominent large-scale underdensity in dark matter maps, reconstructed from gravitational lensing data. Yet controversies remain. Some analyses suggest that even the Eridanus supervoid cannot produce an effect large enough to fully explain the cold spot. If the void were massive enough and empty enough to account for the full temperature anomaly, its existence would itself violate standard cosmological predictions. We would be trading one mystery for another. Alternative explanations for the cold spot range from primordial fluctuations to exotic physics. Some researchers have proposed that the cold spot represents a collision between our universe and an Theo in a hypothetical multiverse. Others suggest it might be a cosmic texture, a remnant of a phase transition in the early universe. None of these explanations has gained consensus, and the cold spot remains one of the most debated anomalies in observational cosmology. The existence of multiple large voids raises important questions. If one supervoid could be dismissed as a statistical fluke, 2 or 3 become harder to explain. Each new discovery increases the tension with standard models that predict such structures should be vanishingly rare. Either we are observing a highly improbable slice of the cosmos, or structure formation produces more extreme features than theory anticipated. Future surveys will discover more voids at various distances and sizes. The Vera Rubin Observatory, currently under construction in Chile, will map billions of galaxies across the southern ski. The Euclid Space Telescope, launched in 2023, is creating a 3-dimensional map of the universe to see how matter has been distributed and pulled apart by dark energy over cosmic time. NASA's Nancy Grace Roman Space Telescope, set to launch in 2027, will provide even sharper measurements. Each void discovered provides an independent test of cosmological predictions. The statistical distribution of void sizes and depths will constrain how structure formation works and whether modifications to standard physics are necessary. The KBC void, Bootes void, and Eridanus supervoid are just the beginning. As our maps of the universe improve, we will build an ever more detailed census of cosmic emptiness and, in the process, learn whether such emptiness is exceptional or routine. Galaxies that form within cosmic voids face unique challenges compared to their counterparts in dense environments. Void galaxies grow up in profound isolation. Unlike galaxies in clusters that interact frequently with neighbours, void galaxies evolve alone, and this environmental difference shapes everything about them. Void galaxies tend to be smaller and dimmer than galaxies in filaments. They contain fewer stars and less overall mass. Many void galaxies qualify as dwarfs, barely massive enough to hold onto their gas against outward pressure from star formation. Their isolation means they rarely experience the galaxy mergers that are common in dense regions. Mergers serve as a primary driver of galaxy evolution elsewhere. They trigger bursts of star formation, feed central supermassive black holes, and transform spiral galaxies into ellipticals. Without mergers, void galaxies evolve more slowly and remain less developed. The star formation rate in void galaxies generally runs lower than in cluster galaxies, but there is a surprising twist. While most void galaxies form stars slowly, a higher fraction of them are starburst galaxies experiencing intense short-lived periods of rapid star creation. This seems paradoxical until you consider gas content. Void galaxies are often unusually gas-rich, containing large reservoirs of neutral hydrogen that have not yet been converted into stars. In dense environments, interactions with neighbouring galaxies can strip away gas or trigger star formation, depleting the reservoir. In voids, galaxies retain their gas longer. When star formation does ignite, perhaps triggered by internal processes rather than external interactions, there is plenty of fuel available. The result is an intense starburst that consumes gas rapidly before settling back into quiescence. The morphology of void galaxies also differs from the general galaxy population. Most are late-type spirals or irregular galaxies rather than ellipticals. Elliptical galaxies form primarily through mergers, which are rare in voids. Without mergers, galaxies maintain their disk structures and spiral arms. Some void galaxies show remarkably undisturbed morphologies, with smooth disk profiles and regular rotation patterns. They have not been battered by gravitational interactions or tides from neighbours. This makes void galaxies excellent laboratories for studying how galaxies evolve in peaceful environments. Observations of void galaxies provide a baseline for comparison with the more chaotic evolution seen in dense regions. Scientists can isolate the effects of isolation itself, separating intrinsic evolutionary processes from environmental influences. Research published in 2023 in the journal Nature confirmed that void galaxies have had slower star formation histories than galaxies in denser large-scale environments. By analysing the spectral properties of galaxies across different cosmic settings, astronomers found that void galaxies form their stars more gradually, never experiencing the rapid assembly episodes common in clusters. Two main star formation history types appear in all environments: short timescale galaxies and long timescale galaxies, but the proportion differs dramatically, with voids hosting far more long timescale galaxies that build their stellar populations slowly over billions of years. One puzzling aspect of void galaxies involves their chemical composition. Stars create heavy elements through nuclear fusion, and when they die, they release these elements into space. Subsequent generations of stars incorporate these elements, gradually enriching the galaxy's overall metallicity. Void galaxies with their slower star formation rates should have lower chemical enrichment compared to galaxies in dense regions. Observations confirm this to some extent. Void galaxies tend to have lower metallicities, but the difference is not as large as expected. Some void galaxies show chemical abundances surprisingly similar to galaxies in normal environments. This suggests that chemical evolution is more complex than simple models predict, perhaps involving gas flows in and out of galaxies that redistribute elements, regardless of environment. The isolation of void galaxies also affects what happens above them. The dark matter halos surrounding void galaxies remain more spherical and undisturbed compared to halos in clusters, which often get stretched and distorted by gravitational tides from neighbouring halos. The simpler halo structure makes void galaxies easier to model and study. However, below a certain mass threshold, halos have too little gravity to retain gas efficiently. Star formation requires gas to cool and collapse, which happens more easily in deeper gravitational wells. The shallowest halos cannot form stars at all, explaining why voids are not completely filled with tiny dwarf galaxies. All of this points to a filter effect operating in voids. The low density prevents certain types of structures from forming. Massive galaxy clusters cannot coalesce because there is not enough matter to pull together. Rich superclusters never emerge. The ceiling on structure development means voids remain perpetually underdeveloped, stuck in an evolutionary state that dense regions passed through billions of years ago. Remarkably, in early 2025, astronomers detected quenched dwarf galaxies even within cosmic voids, where such objects were not expected. These small galaxies had stopped forming stars despite their isolation from the environmental effects that normally shut down the star formation. Their existence suggests that internal mechanisms, not just external environments, can halt star formation in small galaxies. This finding challenges conventional wisdom about galaxy evolution and suggests the physics of the smallest galaxies may be more complex than previously understood. Cosmic voids are the best places in the universe to study dark energy, because voids are the only regions where dark energy dominates completely. In dense areas like galaxy clusters, gravity is strong enough to resist cosmic expansion. Clusters hold themselves together gravitationally despite the universe expanding around them. Even on slightly larger scales in filaments, gravity remains relevant, slowing expansion in those regions. But in voids, gravity becomes negligible. With no significant gravitational pull to counteract it, dark energy controls what happens. voids expand faster than the cosmic average, driven by dark energy's repulsive pressure. This makes voids natural laboratories for measuring dark energy's strength and properties. Dark energy is one of the most mysterious components of the universe. Discovered in 1998 through observations of distant supernovae, dark energy accounts for approximately 68% of the universe's total energy. It behaves opposite to normal matter and gravity. Where gravity pulls things together, dark energy pushes space apart, accelerating cosmic expansion. The exact nature of dark energy remains unknown. It could be a cosmological constant, an unchanging energy density built into the fabric of space itself, exactly as Einstein originally proposed and then retracted as his greatest blunder. Or it could be a dynamic field that varies in strength over time and space. Distinguishing between these possibilities requires precise measurements of how expansion accelerates in different environments and at different cosmic epochs. Voids provide a cleaner signal for these measurements than dense regions. In clusters, gravity complicates everything. Local gravitational pulls from nearby masses affect galaxy motions, making it hard to separate cosmic expansion from local effects. In voids, those complications are minimal. Galaxies move almost entirely due to cosmic expansion and dark energy. By measuring how fast voids expand compared to predictions, scientists can test whether dark energy behaves as a constant or changes. Another way voids help involves their shape. Dark energy affects not just how fast the universe expands, but how it expands in different directions. If dark energy is truly uniform, voids should expand equally in all directions, remaining spherical. But if dark energy has variations, or if unknown forces act differently along different axes, voids might expand more in some directions than others, becoming elongated or distorted. Current observations show that most large voids are roughly spherical, supporting uniform dark energy. But measurements are not yet precise enough to rule out small variations. Improved surveys will provide much better shape measurements in coming years. The expansion history of voids encodes information about dark energy's past behavior. Voids have been growing for billions of years, and their current size reflects that entire history. By modeling how a void should grow over time given different dark energy properties, scientists compare predictions to observations. If dark energy was weaker in the past and strengthened recently, voids would have grown slowly at first and then accelerated. If dark energy has been constant, voids should grow at a steady accelerating pace determined by that constant value. Some researchers have proposed that dark energy might not exist at all. Instead, the apparent acceleration of cosmic expansion could result from the dominance of voids in the cosmic landscape. Because voids expand faster than dense regions due to their lack of gravitational resistance, and because voids make up most of the universe's volume, the average expansion rate we measure is dominated by void expansion. This timescape model suggests that what we attribute to dark energy might actually be an illusion created by cosmic structure. A study published in late 2024 analysed data from the Pantheon Plus survey, the most comprehensive collection of Type Ia supernovae ever assembled. The researchers found that the timescape model fits the data comparably to standard dark energy models. Professor David Wiltshire, who led the study, stated that their findings show dark energy may be a misidentification of variations in expansion energy, which is not uniform in a universe as lumpy as ours. If voids create the appearance of acceleration without requiring a mysterious repulsive force, the implications for physics would be profound. Dark energy, one of the cornerstones of modern cosmology, might be a measurement artifact rather than a real phenomenon. Whether dark energy is real or illusory, the future of voids is one of increasing dominance. As the universe continues expanding, voids will grow faster than everything else. They will consume more and more volume as filaments thin and clusters become increasingly isolated. Billions of years from now, the cosmos will be even emptier than it is today, with voids making up an ever larger fraction of total space. On even longer timescales, trillions of years into the future, structures that are not gravitationally bound will drift apart entirely and lose all contact. The cosmic horizon, the boundary beyond which light cannot reach us, will shrink as expansion accelerates. Objects currently visible will fade from view as their light gets redshifted into invisibility. Galaxies deep within voids will find themselves in increasingly empty skies. A civilization arising in a void galaxy far in the future would face profound cosmological isolation. Their sky would be nearly empty except for their local group. The The cosmic microwave background would have stretched beyond detectability. There would be no evidence of the Big Bang, no distant galaxies to measure expansion, no way to learn about the larger cosmos. Such civilizations might conclude they live in a small static island universe surrounded by nothingness, never suspecting the vast structure that once existed. The fate of the universe is void domination. The cosmic web we observe today, with its intricate filaments and clusters, is a temporary phase. The true long-term structure is emptiness punctuated by isolated islands of matter, growing ever more remote from each other. We live in an unusual time when the universe still has rich structure, and when voids are features rather than the dominant reality. Billions of years hence, voids will be everything. We are inside a cosmic hole 2 billion light-years wide. This is not metaphor or speculation. This is observation. The KBC void is real. Its effects are measurable. Its existence challenges fundamental assumptions about cosmology and our place within the universe. The discovery forces us to confront uncomfortable truths. Our location may not be typical. Our measurements may be systematically biased. Conclusions we have drawn about the cosmos might require revision as we learn more about the void that surrounds us. The Hubble tension remains unresolved. Whether the void fully explains the discrepancy between local and cosmic expansion measurements, or whether new physics is required, future observations will eventually determine. What we know with certainty is that something is wrong with our picture of the universe, and the void stands at the center of the controversy. Throughout scientific history, each generation has believed it was approaching a complete understanding of nature, only to discover that deeper mysteries awaited. The void reminds us that the universe still holds surprises. Despite decades of precision cosmology, despite satellites mapping the cosmic microwave background with exquisite accuracy, despite telescopes surveying millions of galaxies, we miss the fact that our entire cosmic neighborhood is abnormally empty. What else might we have overlooked? The philosophical implications are profound. The cosmological principle which served as the foundation of modern cosmology may apply only approximately on scales we are just beginning to probe. If large voids like the KBC void are more common than theory predicts, the universe is lumpier than we assumed. If they are as rare as calculations suggest, our position is extraordinary. Neither option is entirely comfortable. Some scientists have proposed that resolving these puzzles might require modifications to our theory of gravity. Einstein's general relativity has passed every test thrown at it for over a century. Yet it struggles to explain how structures as large and deep as the KBC void could form from the initial conditions we believe existed after the Big Bang. Perhaps gravity behaves differently on cosmological scales than we think. Perhaps dark matter has properties we have not anticipated. The void may be pointing toward revolutionary physics. What does it mean to exist in the cosmic outskirts? In dense regions of the universe, galaxies interact constantly. Stars form rapidly, matter cycles through successive generations of stellar birth and death, enriching the cosmos with heavy elements. Galaxy clusters blaze with hot gas radiating X-rays. It is a chaotic, energetic environment. Our void is different. Galaxies evolve slowly here. Star formation proceeds at a measured pace. The gravitational tides that transform galaxies elsewhere are largely absent. In some ways, the void provides a more peaceful environment than denser regions. Catastrophic events like nearby supernovae or gamma-ray bursts that could sterilize planets are less common. The isolation offers long-term stability. Whether this affects the prospects for life is unknown. Perhaps void environments are more hospitable for complex life to develop because they offer stability. Perhaps they are less hospitable because fewer heavy elements are available for planet formation. The question remains open. What is certain is that our view of the cosmos is shaped by where we observe from. Light reaching our telescopes has passed through the void on its way to Earth. The distribution of matter we see is filtered through our unusual position. The expansion rate we measure is influenced by local gravitational effects. We are not neutral observers standing outside the system. We are participants, embedded within the very structure we are trying to understand. This realization should inspire humility. The universe does not exist to be comprehensible. It does not arrange itself for our convenience. We have worked for generations to decode its secrets, and we have made remarkable progress, but the void reminds us that our understanding remains incomplete. There is always more to learn, always deeper mysteries awaiting discovery. As you go about your day, remember that you are falling through a hole in space. Not metaphorically, but actually. Every second, you move hundreds of miles relative to the void's center, pulled by distant gravity toward the denser regions of the cosmic web. The universe is carrying you along on a journey that began before Earth existed and will continue long after. The void is our home, it shapes what we see, affects what we measure, and may be hiding fundamental truths about the cosmos that we are only beginning to glimpse. What other secrets might it hold? If this journey through cosmic emptiness has changed how you see our place in the universe, consider sharing it with others. Hit that like button. Subscribe to the channel. Join us next time as we continue exploring the strange and wonderful cosmos we call home. Until then, keep looking up and remember, the greatest discoveries are still waiting to be made. To truly understand how we came to live inside a cosmic void, we must travel back to the very beginning. Not just billions of years, but to the first fraction of a second after the Big Bang. When the universe was smaller than an atom and quantum mechanics ruled supreme, in that primordial instant something extraordinary happened. The universe underwent a period of exponential expansion called inflation. In less than a trillionth of a trillionth of a trillionth of a second, the cosmos expanded from something unimaginably small to something macroscopic. This expansion was so violent and so rapid that it stretched quantum fluctuations, the inherent jitteriness of empty space at the smallest scales, to cosmic proportions. Quantum mechanics tells us that even in a perfect vacuum, particles constantly pop in and out of existence. Virtual particles materialize from nothing, exist for impossibly brief moments, and then vanish again. This is not speculation, but experimentally verified physics. The Casimir effect, where two metal plates placed very close together feel an attractive force from the exclusion of virtual particles between them, confirms that empty space seethes with quantum activity. During inflation, these quantum fluctuations became locked into the fabric of space itself. Regions where slightly more virtual particles happened to exist at the critical moment ended up slightly denser. Regions with fewer virtual particles became slightly less dense. The differences were minuscule, perhaps 1 part in 100,000, but they were enough. When inflation ended and the universe continued expanding at a more sedate pace, those density variations began their long journey toward becoming the cosmic structures we observe today. Gravity, though weak, never rests. It pulled matter toward the denser regions, slowly but inexorably. Over millions and then billions of years, the small advantages compounded. Dense regions became denser, sparse regions became sparser. The cosmic microwave background radiation provides our clearest snapshot of these primordial fluctuations. Released when the universe was 380,000 years old and finally cool enough for atoms to form, this radiation carries the imprint of those earliest density variations. Temperature differences in the microwave background correspond directly to density differences in the early universe. Warmer spots were slightly denser. Cooler spots were slightly less dense. Satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have mapped these temperature variations with extraordinary precision. The maps reveal a nearly random pattern of hot and cold spots at various scales, exactly what you would expect from amplified quantum fluctuations. This is one of the most profound confirmations in all of science. The largest structures in the universe originated from quantum uncertainty in the first moments of existence. But here is where the puzzle begins. Standard inflationary models predict that the quantum fluctuations should follow a specific statistical distribution. Small variations should be common, large variations should be rare. The probability decreases sharply as the size of the fluctuation increases. When cosmologists run simulations using these predicted distributions, they can reproduce the general features of the cosmic web. Filaments form, clusters condense, voids emerge. The statistics of these structures match observations remarkably well on most scales. Yet the KBC void seems to require an initial fluctuation that was unusually large and unusually negative. For a void this size and this deep to form naturally, the region that would become our cosmic neighborhood must have started out significantly less dense than almost anywhere else in the observable universe. The probability of such a large negative fluctuation is low enough to make cosmologists uncomfortable. Several possibilities present themselves. Perhaps inflation was not as smooth as standard models assume. Some inflation models predict an enhanced power spectrum at large scales, meaning big fluctuations are more likely than simple models suggest. If the universe experienced multiple phases of inflation, or if inflation ended in a particular way, the resulting fluctuations could have properties different from standard predictions. Alternatively, perhaps our understanding of how fluctuations grow into structures is incomplete. The standard model assumes that dark matter is cold, meaning its particles move slowly compared to the speed of light. Cold dark matter produces a specific pattern of structure formation, but if dark matter has properties we have not anticipated, perhaps interacting with normal matter in subtle ways or having a small fraction of warm particles that move faster, structure formation could proceed differently than expected. A third possibility is that we simply got lucky. Random processes produce outliers. In a universe vast enough, extremely rare events will happen somewhere. We could be observing from inside one of those rare events, living in a cosmic environment that most other observers in most other locations would never experience. Each of these possibilities carries implications for fundamental physics. If inflation deviated from standard models in ways that produce the KBC void, studying the void could reveal new physics from the earliest moments of the universe. If dark matter has unexpected properties, the void could help us understand what most of the universe is actually made of. Even if we simply got lucky, confirming that explanation would tell us something important about the statistical nature of cosmic structure. The quantum origins of the void connect our everyday existence to the most fundamental processes in nature. The emptiness surrounding our galaxy traces back to random fluctuations in a universe smaller than a proton. We are, in a very real sense, children of quantum chance, living in a region of space shaped by events that occurred before time itself had meaning in any conventional sense. Confirming the existence and properties of the KBC void presents formidable observational challenges. You cannot simply photograph emptiness. The void reveals itself only through careful measurement and statistical analysis, requiring astronomers to count galaxies, measure their distances, calculate their motions, and compare everything to theoretical predictions. The primary evidence comes from galaxy surveys. Over decades, astronomers have systematically catalogued millions of galaxies, recording their positions on the sky and measuring their redshifts to determine distances. The Sloan Digital Sky Survey alone has mapped more than 2 million galaxies across a significant fraction of the visible sky. These surveys provide the raw data for constructing three-dimensional maps of cosmic structure. When researchers analyze these maps, they count how many galaxies appear in volumes at different distances from Earth. They then compare these counts to what standard cosmology predicts. The prediction involves running computer simulations of structure formation starting from the initial conditions revealed by the cosmic microwave background, then calculating the expected galaxy distribution at the present epoch. The comparison reveals the void. Within about 1 billion light-years, there are systematically fewer galaxies than predicted. The deficit is not huge, roughly 20% fewer than expected, but it is statistically significant and extends in every direction. The spherical symmetry of the underdensity, centered approximately on our location, distinguishes it from ordinary voids in the cosmic web, which would appear in particular directions rather than surrounding us uniformly. Measuring the void's exact depth and extent proves more difficult. Different surveys use different techniques and probe different types of galaxies. Some surveys focus on bright galaxies that are easy to detect. Others go deeper to find fainter galaxies but cover smaller areas of sky. Reconciling results from different surveys requires careful accounting for selection effects and systematic biases. One important cross-check comes from baryon acoustic oscillations, the imprint of sound waves that travelled through the early universe. These oscillations left a characteristic pattern in how galaxies are distributed, with a slight preference for separations of about 490 million light-years. By measuring this pattern at different cosmic epochs, astronomers can trace the expansion history of the universe with high precision. Recent baryon acoustic oscillation measurements have provided strong support for the void hypothesis. Analysis of data collected over 20 years shows that expansion appears faster in our local region than at greater distances, exactly what the void would predict. The statistical significance of this result is striking. According to researchers presenting at major conferences in 2025, a model including the void fits the data far better than models assuming uniform cosmic density. Another line of evidence comes from galaxy peculiar velocities. Galaxies do not just recede from us due to cosmic expansion, They also have individual motions caused by local gravitational effects. By measuring both the redshift, which includes expansion plus peculiar velocity, and the distance, which depends only on position, astronomers can extract the peculiar velocity component. Maps of galaxy peculiar velocities reveal coherent flows across hundreds of millions of light years. Galaxies are streaming away from underdense regions and toward overdense regions, exactly as gravity predicts. The magnitude and pattern of these flows are consistent with the presence of a large void centered near our location. Critically, the void model predicted these bulk flows before they were precisely measured, lending additional credibility to the hypothesis. The cosmic microwave background provides yet another constraint. Light from the CMB passes through the void on its way to Earth. The integrated Sachs-Wolf effect should cause a slight temperature depression in the direction of any large void, though the effect from the KBC void specifically is small and difficult to separate from other contributions to CMB temperature variations. Despite the mounting evidence, not all cosmologists are convinced. Some point to potential systematic errors in galaxy surveys. Perhaps certain types of galaxies are underrepresented in our catalogues for technical reasons unrelated to cosmic structure. Perhaps the comparison between observations and simulations involves subtle biases that inflate the apparent void significance. Others note that independent groups using different data and different methods have sometimes obtained different results for the void's properties. While most studies find evidence for local underdensity, the exact depth varies from analysis to analysis. If the true deficit is only 10 or 15% rather than 20%, the statistical tension with standard cosmology becomes less severe. Resolving these questions will require better data. Future surveys like those from the Vera Rubin Observatory will map billions of galaxies with unprecedented completeness. The Dark Energy Spectroscopic Instrument is measuring redshifts for tens of millions of galaxies to create the most detailed three-dimensional map of the universe yet attempted. These surveys will either confirm the void's extreme properties or reveal that current estimates are too pessimistic. The challenge of measuring the invisible illustrates a broader truth about cosmology. We cannot step outside the universe to view it objectively. We are embedded within it, limited to observations from a single location in space and time. Every measurement we make is filtered through our local environment. The void reminds us how much that environment might matter. If we truly live inside a cosmic void, what might that mean for the prospects of life elsewhere in the universe? While any conclusions remain speculative given how little we understand about the origins of life, the void's unusual properties could affect habitability in ways that cosmologists are only beginning to consider. One possibility involves isolation. Galaxies in voids are separated by greater distances than galaxies in dense regions. If life exists elsewhere in our cosmic neighborhood, based on what we know about galaxy distribution, it would more likely be found in other void galaxies, which are themselves sparse and widely scattered. Communication between civilizations would face even longer delays and greater technological challenges than the already formidable barriers that cosmic distances impose. But isolation might also offer advantages, at least in principle. Dense galaxy clusters are violent places. Galaxies collide and merge frequently. Tidal forces from neighboring galaxies can disrupt planetary systems. Active galactic nuclei at the centers of cluster galaxies emit intense radiation that could potentially sterilize nearby worlds. Galaxy clusters also contain hot intracluster gas that strips away the cold gas reservoirs galaxies need for sustained star formation. Void galaxies experience none of these disruptions. They evolve peacefully, maintaining stable star formation over billions of years. This suggests that planetary systems forming in void galaxies might face fewer external threats to their long-term stability. A planet could theoretically orbit its star for billions of years without experiencing the gravitational upheavals that frequently disturb planets in cluster galaxies. The lower rate of supernovae and gamma-ray bursts in voids could also, in theory, favour life. These energetic events pose potential extinction risks for biospheres on nearby planets. A sufficiently close supernova could strip away a planet's atmosphere or bombard its surface with lethal radiation. The lower density of stars in voids means any given planet likely faces a reduced frequency of such nearby catastrophes. However, voids also present challenges. The slower star formation rate means fewer opportunities for life to arise in the first place. Heavy elements necessary for rocky planet formation, like iron, silicon, and oxygen, are created in stellar fusion and distributed by supernovae. Lower star formation means less production and distribution of these elements. Void galaxies tend to have lower metallicity than cluster galaxies, which could limit the raw materials available for building Earth-like worlds. The relationship between cosmic environment and habitability remains poorly understood. We have only one example of a planet where life arose, and that example happens to reside in a void. Whether our void location is relevant to Earth's habitability, or merely coincidental, cannot be determined from a single data point. Some researchers have speculated about more exotic possibilities. If large voids are genuinely rare, then most intelligent observers in the universe would live in more typical environments. Finding ourselves in a void might be evidence of anthropic selection, suggesting that voids provide conditions favourable for observers that denser regions do not. But this reasoning is circular and difficult to test. What seems clear is that the cosmic environment matters. Where you live in the universe affects what you can observe, what resources are available, and what threats you face. The void is not just an abstract cosmological curiosity. It is the stage on which our entire evolutionary history has played out, shaping the conditions that allowed Earth to form and life to emerge. If intelligent civilizations exist in void galaxies throughout the cosmos, they might all share a similar predicament to ours. They would measure local expansion rates that appear anomalously fast. They would find themselves surrounded by unusual emptiness. They might wonder, as we wonder, whether their cosmic location is significant or merely random. The void connects questions about the largest scales of the universe to questions about life's place within it. Understanding one may help us understand the other. The next decade will bring unprecedented data to bear on the void hypothesis and the Hubble tension it might explain. Multiple major astronomical projects are either underway or about to begin, each designed to probe cosmic structure and expansion with greater precision than ever before. The Dark Energy Spectroscopic Instrument installed on the Mail telescope in Arizona began full scientific operations in 2021. Over 5 years, it will measure precise redshifts for more than 30 million galaxies and quasars, creating the largest three-dimensional map of the universe yet constructed. This map will trace Brion acoustic oscillations and galaxy clustering to unprecedented distances, allowing researchers to test whether expansion truly varies between our local region and the distant cosmos. The Vera Rubin Observatory in Chile, expected to begin its 10-year survey soon, will photograph the entire southern sky repeatedly with a camera containing over 3 billion pixels. Over its operational lifetime, it will detect and catalogue tens of billions of galaxies, dwarf galaxies, and other objects too faint for previous surveys to detect. This comprehensive census will reveal whether the apparent underdensity in our region extends to the faintest galaxy populations, or is an artifact of incomplete sampling. The Euclid Space Telescope, launched by the European Space Agency in 2023, is specifically designed to study dark energy and cosmic structure. By combining visible light imaging with infrared observations, it will measure galaxy shapes and positions across more than a third of the scan's. Gravitational lensing measurements from Euclid will reveal how dark matter is distributed in 3 dimensions, providing an independent check on the void's reality that does not rely on counting luminous galaxies. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will complement these efforts with even sharper infrared observations. Its wide-field instrument can image an area of sky nearly 100 times larger than the Hubble Space Telescope at comparable resolution, enabling efficient surveys of distant supernovae and galaxies. Roman will help determine whether the Hubble constant measured locally truly differs from the global value. These instruments will not merely refine existing measurements, they will open entirely new windows on cosmic structure. Machine learning algorithms trained on their vast datasets will identify patterns invisible to traditional analysis. Cross-correlations between different surveys will reveal systematic effects and eliminate spurious signals. The statistical power available to astronomers will increase by orders of magnitude. Within 5 to 10 years, we should know with high confidence whether the KBC void is real and whether it can fully explain the Hubble tension. If the void proves genuine and its effects match predictions, cosmology will have gained an important insight. Our local measurements are not representative of the universe as a whole, and the cosmological principle applies only approximately on scales comparable to the void's size. If instead the void turns out to be a measurement artifact, or if its effects prove insufficient to resolve the Hubble tension, cosmology will face a different challenge. New physics beyond the standard model might be required. Dark energy might behave differently than the cosmological constant predicts. The early universe might contain surprises we have not anticipated. Either outcome will advance our understanding of the cosmos. Science progresses by testing hypotheses against data, and the data coming in the next decade will be decisive. The void hypothesis has made clear predictions that can be confirmed or refuted. That is how science is supposed to work. Whatever the surveys reveal, one conclusion seems inescapable. The universe is stranger and more complex than early cosmologists imagined. Simple models with smooth, uniform distributions of matter cannot capture the full reality of cosmic structure. We live in a cosmos of walls and voids, filaments and clusters, where location matters and observations depend on where you observe from. The void, whether it ultimately explains the Hubble tension or not, has already taught us this lesson. It has forced cosmologists to take seriously the possibility that our cosmic neighborhood is unusual. It has motivated new observations, new analyses, and new theoretical ideas. Even if it fades from prominence as data accumulate, the void will have served its scientific purpose, pushing our understanding forward by challenging what we thought we knew. We began this journey with a simple statement: you are falling through a hole in space 2 billion light years wide. Now, having traversed the discovery of the void, explored its physical properties, examined its implications for the cosmology, and considered what it means for our place in the universe, that statement carries richer meaning than it did before. The void is not just emptiness, it is a structure, one of the largest coherent features in the observable cosmos. It has boundaries, properties, and effects. It shapes the motion of galaxies, influences the light we receive from distant sources, and may be distorting our most fundamental measurements of cosmic expansion. The void is as real and as significant as the filaments and clusters that surround it. Living inside the void means living with uncertainty about how typical our observations are. For a century, cosmologists have assumed that measurements made from Earth represent universal truths. The void challenges that assumption. It suggests that our location, far from being unremarkable, might be one of the most unusual in the observable universe. Whether that unusual location matters for our fundamental conclusions about cosmology remains to be determined. The void also connects the smallest scales to the largest. Quantum fluctuations in the first moments after the Big Bang, amplified by inflation and sculpted by billions of years of gravitational evolution, produce the cosmic structure we observe today. We are, quite literally, the descendants of quantum randomness, living in a region of space whose emptiness was determined before atoms existed. Perhaps most profoundly, the void reminds us of our cosmic context. Daily life occurs on scales of meters and minutes. Our concerns involve people, places, and events confined to a thin film on the surface of one planet. But that planet orbits a star in a galaxy that is rushing through a void at hundreds of kilometers per second, responding to gravitational forces from structures millions of light years away. We are participants in cosmic processes that dwarf anything in human experience. This perspective can evoke wonder, humility, or insignificance, depending on your temperament. What it should not evoke is indifference. The universe has presented us with a puzzle. Our best measurements of cosmic expansion disagree with each other. One possible explanation puts us inside a cosmic void that affects what we can measure. Whether this explanation proves correct or not, the puzzle demands our attention. Science thrives on such puzzles. They mark the boundaries of current understanding and point toward new discoveries. The Hubble tension and the void hypothesis that might resolve it represent exactly this kind of frontier. We do not yet know the answers, but we know how to search for them. Observations, analysis, theoretical development, and testing against data will eventually resolve the question. In the meantime, we live with mystery. We live inside a void whose existence challenges expectations, whose origin traces to quantum processes in the early universe, and whose influence might be distorting everything we thought we knew about cosmic expansion. The void surrounds us in every direction, extending for hundreds of millions of light years, containing our galaxy, our solar system, and our planet. You are falling through that void right now, as you were when this video began. You will still be falling through it when it ends. The universe carries us along on its eternal expansion, and the void shapes our view of everything beyond. If this exploration has sparked your curiosity about the cosmos, share it with someone else who might appreciate the wonder. Like this video, subscribe to the channel. Together, we can continue exploring the strange, beautiful, and mysterious universe we call home. Until next time, keep looking up. The void is watching back.